with this last session is about something called alpha method and beta method to design piles, basically. So in particular, I will be focused the explanation about driven piles in sand, but actually the methods are alpha method and beta method are the same methods. They are called differently to distinguish between a problem when you have clay or a problem when you have sand. So, and remember that when you have clay, you will have a condition of undrained condition. And when you have sand, you will have a drain condition in your problem. So the first things I wanted to tell you in this presentation for the lesson today is that it's very useful for you if you review and you understand in every single details the concept of effective stress, because we are going to calculate the effective stress to determine the capacity of our pile. So you have this video about effective stress with all the things you need to know. And it's something that we have covered already in a lesson during the semester. But you have the link in there to go and to review in the YouTube channel the concept of effective stress that we are going to use in the determination of the capacity of our pile in the lesson today. So the important thing to remember is that the effective stress is equal to the total stress minus the pore water pressure. And to be able to sketch this pressure in a diagram that usually is a linear diagram because it's hydrostatic pressure, and to be able to determine the value of the effective stress at every level, and especially important in piles because a pile is an structure that goes deeper in the soil. So in the first place, we need to understand when we are talking about piles, what type of structures is a pile. A pile is an structure that is very similar to a column that is inserted in the soil with different methods. You can have a driven pile or you can have a bore pile where you make first the hole that will contain the pile and after you pour the concrete in there, for example, or you install the steel pile in there. And the driven pile is driven in the soil using a hammer and a hydraulic hammer, as you saw in the videos during the last week or the week before. I don't remember exactly. But basically, you have a sort of column. In this case, for example, let's think that our pile is only one pile that is a driven pile, so was installed by a hydraulic hammer. Have a cross section, a circular cross section. So we have the diameter in this case. And we have identified as well the loads that are discharged on this pile, that this pile has to spread on the soil. So we have the distinction between the variable unfavorable loads and the permanent unfavorable load in this case. So it's the same sort of assumption or the same sort of information we have in terms of load as in a shallow foundation. The other thing that this problem that we'll explain will include is the location of the water table, because we cannot, let's say, think about a problem without a water table when we have a pile, because the pile is certainly an structure that goes deeper. So you will find for sure the water table at some level. So the presence of the water table will produce the needs of calculating the effective stress because there will be pore water pressure in the first place. And on the other hand, even when you have only a soil, let's say in this problem, we have only sand as the only layer of soil you have that is receiving the pile, but the water table will divide the soil in two areas, so in two layers. A first layer on top with the sand dry, and another layer of soil that is submerged in water, so it's saturated in water. So this will distinguish two areas that will work differently. So you will need a dry unit weight for the sun and the saturated unit weight for the sun as well to resolve the problem. We are going to need as well the definition of some coefficients depending on the method we are going to use. For example, for sun, we are going to use something called the beta method. So we'll need the value of beta. And we're going to need an NQ as well. And this NQ is related with the bearing capacity of your soil. And it's exactly the same coefficient we have used for shallow foundations. So we are going to have this information. In terms of the Eurocode, what we're going to need is the same thing we have been used for shallow foundations and walls and slow stability as well. So we are going to say that following the advice of the Eurocode 7, we are going to use the design approach 1 combination 2. So we are going to use the columns of the subsequent tables as indicated in this table in here. So for example, the only thing we are going to use for piles will be the increment in the actions. So we are going to use the column A2 for the table related with actions. And the only coefficient differently to 1 will be the one for variable and favorable action, that is 1.3, because the other coefficients are ones and zeros. And we are not going to have generally, at least in the problems we're going to tackle in this module, variable favorable actions. So we are going to have only permanent unfavorable actions and variable unfavorable actions. So we are going to use these two coefficients, 1 and 130. Because we're talking about piles, there will be an extra table to use if you compare the process with the shallow foundations. That are, this table is called the UK National Annex because it's an additional table that gives us certain factors to reduce the capacity of the piles to cover our back in terms of what we sign in terms of capacity of these piles. So there are several coefficients depending on if the pile is bored or if the pile is driven. And there is a coefficient that is used in every case that is because the model, and this means that we have to reduce in this 40% or using this 1.4 in here. So dividing the capacity we calculate to reduce this capacity, considering that this is a calculation we make using a model, is a very simple model. But because it's not exactly the reality, we need to reduce this capacity in order to follow the advices of the Eurocode 7 and to be safer when we make a decision and we sign a design, for example. Depending if the pile is bored or is driven, we have different coefficients to reduce the capacity at the base of the pile and in the shaft of the pile. So you see that the coefficients for bored piles are bigger because there is more uncertainty regarding the capacity of a bored pile than in the case of the driven pile. This is the reason why there is this difference in the coefficients. But in both cases, we need to reduce the capacity we calculate following the alpha method or beta method in order to be safer because we have uncertainty in terms of reality and the model we use to design these structures. So basically, we are going to study only two methods. There are more methods to design and to check the capacity of the piles, but we're going to use these two simple methods that are called alpha methods and beta methods. And as you can see on the screen, let's say the shape of the two equations to define the capacity of the pile are very similar because the concept is exactly the same as we are going to see in a minute. Some two cases are distinguished in here. So the clay and drain capacity and the sand drain capacity. We are going to call Q the capacity, and the capacity will be made in kilonewtons. And you can see that there are two terms in here that are different. in both cases. For example, for the alpha method, you have a first term that can have inside, several terms depending on the value of this n. This summation in here, n represent the number of layers you have. For example, in the problem I have shown at the beginning, we are going to have only 2 layers, a layer of sun-dry and a layer of sun-saturated. And this first factor in here in these brackets, you can recognize easily that is basically 2 pi times r is the perimeter of a circle. L is a length. So this is the area of the shaft of the pile. In the layer you are analyzing the capacity. Alpha is a coefficient that give you the possibility to define the capacity using the friction between the shaft and the soil. And this friction or this capacity in friction will depend as well on the undrained strength of the clay. And this means average because the strength of the clay will be different at the ground surface and is going to be greater and greater when you go deeper and deeper in the soil. This is the reason why this value is an average. So this term then, this first term is related with the friction that the pile has with the soil, and is the capacity because the friction. And the second term is the bearing capacity we have studied for shallow foundations at the tip of the pile, because the pile will have a circular cross-section, for example, or independently of the shape of the section, you will have an area. In this case, we are considering that the pile is circular. And in the majority of the cases, the piles are circular, but there are other cross sections. So this is the area of a circle in this case. This NC is the bearing capacity or a coefficient that allows you to calculate the bearing capacity when you have a clay. And this is again the undrained strength of the clay, but in this case is the undrained strength of the clay at the base of the pile, so at the tip of the pile, because this is going to be the deepest location of the pile in this case. So you see then that the formula to calculate the capacity in the alpha method is called alpha method because you have this coefficient alpha here, is basically the resistance because the friction plus the resistance because the bearing capacity at the tip of the pile. If you study the formula for the sand, where you have a drain condition because the sand have allow the water to flow because the permeability, you have the same structure. So you have in the first term, the area of the shaft that is in contact with the soil. You have the coefficient beta in this case. And instead of having the strength of the clay, because this is sand, what you have is the effective stress at that layer as an average to that's contribute with the resistance in terms of friction. So the bigger is the effective stress, the better will be the friction between the sand and the pile. And at the tip of the pile, again, you have the area of the circular section of the pile, a coefficient that is related with the bearing capacity for sand and Q. And again, you are going to use the effective stress at the base of the pile because this is the location where you are establishing the bearing capacity of this pile in sand. So the structure, again, for these two formulas to evaluate the bearing capacity, not the bearing capacity, the total capacity of the pile are divided in 2 terms in general. The first term is related with the friction. The second term is related with the bearing capacity. But the first term can have several terms inside again. This is the reason why you have this summation in here, because you can have several layers of soils. In our case, it's going to be simple because we are going to have a dry soil and a saturated soil only. But you can have more layers in a problem. For example, you can have a layer of sand, you can have a layer of clay, and you can have another layer of sand, 3 layers of soils, and some of them will be underwater, some of them will be dry, depending on the location of the water table. So this N could be 2, 3, 4, 5, depending on the length of the pile and depending on the distribution of layer you have in your soil. But for our problems will be simple and will be no more than 2 layers. So don't worry about that. So this is our problem then. So we have a pile, we have the information about the loads. So we have a variable unfavorable load of 150 kilonewtons. We have a permanent unfavorable load of 300 kilonewtons. We are going to assume that the unit weight of the water is 10 kilonewton per cubic meter. We are going to have a soil that is sand, that when it's dry have a unit weight of 19 kilonewton per cubic meter. We know the location of the water table at 4 meters from the ground. We know the diameter of the pile is half a meter. We know as well the saturated unit weight for the sand, which is 21 kilonewton per cubic meter. And we have been provided with the coefficients we need for the beta method in this case, because this is sand and drain, sorry. So you have the beta equal to 0.3 and NQ is equal to 60. So you have all the data to resolve this problem. So the idea of this problem is to determine if this pile is in good condition or we need to redesign the pile to have a better capacity. So we need to compare the total load we have and is this soil is able to take all this load that the pile is going to spread. Because remember that in geotechnical engineering, we are not designing the pile itself. So we are not checking the stresses on the pile, on the reinforced concrete, for example, of this pile. What we are doing is we are analyzing what happened in the ground, so in the soil that is in contact with the pile in terms of frictions, what happened in terms of the bearing capacity. So we are establishing here if the soil is able to take the loads that the pile is distributing from the building. And this is what we call the capacity of the pile in this case. It's not the capacity of the pile itself, it's the capacity of the soil that is receiving the loads because of the pile. So we are going to use the beta method then. And again, just to clarify, remember that the first term is related with the friction that the pile has undeveloped with the soil, and this gives the pile certain capacity to spread loads. And the second term is related with the bearing capacity at the tip, at the end of the pile in here where I'm showing with the pointer. So in terms of the something we call the design load in piles, that is the total load that the pile has to distribute in the soil, is equal in this case to the permanent unfavorable load multiplied by 1. This one is because the Eurocode, so it should be in red as well. And this coefficient 1.3 is the other coefficient that the Eurocode 7 advised for the variable unfavorable load. So we are going to increase in 30% the unfavorable load. And applying these coefficients, we found that the maximum load that this pile will receive from the building is 495 kilonewtons. You can think as well in the self-weight of the pile. In here, we are not including the self-weight of the pile because it's not considerable. We are assuming that it's not going to make a big difference. But if you want to include the self-weight of the pile, you can include it in here because you know the dimension of the pile. So multiplying by the unit weight of the reinforced concrete, which is usually 24, 25 kilonewton per cubic meter, you can add the loads of the pile itself to this design loading here, and should be advisable to take into consideration. But anyway, we are going to say that this is the load we need to distribute in the soil. This will be the load that we are going to use in this exercise to compare with the capacity. And now we need to start calculating the effective stress we have, because the effective stress will define in some way the capacity of these piles in friction and in terms of bearing capacity as well. As you see in the formula, we need to establish the value of the effective stress and as an average in here in the first term and at the base in the second term. So at 4 meters, where the water table is located, we are going to have certain value for this effective stress. The effective stress will start at 0 in the ground and will reach this value at the base of this triangle on the screen. And in this case, because it's the total stress minus the water pressure, what we are going to have in terms of the stress is the total stress, which is 19 is the unit weight of the sun, multiplied by 4 is the stress or the pressure of the ground at this level, minus 0 because the water table is located here, so we don't have water from the ground to the 4 meters depth. So this effective stress will be equal to the total stress, equal to 76 kilonewton per square meter. And this is the value at the base of this triangle in here, but we need the average. The average will be 0 plus 76 divided by 2, or 76 divided by 2, which is this 38 kilonewton per square meter in here. So basically, we have established two values of the ground pressure. The pressure, the effective stress, or the pressure, or the effective pressure at the base of this triangle, 76, and the average 38. That is, these two values are going to be used in this formula, because in here we need the average, and in here we need at the base, but this is not the value we're going to use. The other thing we need to evaluate the capacity is the area of the shaft. So it's the area of the shaft of this pile. So the area, the lateral area of the cylinder you have in here. So basically will be pi times the diameter 6.28 square meter as the area of the shaft in this first layer of this pipe. But we need to continue calculating more effective stress for the second layer. So for example, if we want to establish the value of the average effective stress in this area in here, we need to calculate first the effective stress at the base of this triangle in here, so at the end of the pile. And for doing that, what we have is basically the previous one, 19.4 is the dry unit weight of the sun multiplied by 4 is the stress in here, or the pressure in here, plus 21 is the saturated unit weight of the sun from the location of the water table and down, multiplied by 11, which is the difference between the total length of the pile minus 4 meters, because we are considering now from here to the end, and minus the unit weight of the water times 11, because we need to diminish the pore water pressure to calculate the effective stress. So this will be the value then of the effective stress at the base of the pile is 197 kilonewton per square meter. We have made the total stress minus the pore water pressure at the base. And now, because we need the average, we need to do the average between 76, the effective stress we have calculated for the previous layer, plus 197, the effective stress we have calculated at the base, divided by 2 will give us 137 kilonewton per square meter, which is the average for the second layer of this problem. We need to calculate as well the area of the shaft for the second layer, which is basically the same thing as before, is pi multiplied by the diameter, multiplied by 11 meters, because 11 meters is from where the water table starts until where the piles end. And this value is 17.27 square meter. One more thing we're going to need at the base is the area of the base of the pipe, which is basically a circle. So pi times the radius square is equal to 0.196 square meter, which is the area of the cross section of these piles that will be useful for us in this formula in here to establish the bearing capacity of the pile at the tip. So now we have all the information regarding the effective stress and regarding the areas of the shaft and regarding the location of the several sections we need in this pile. So we need to fit, or we are able to fit this formula to establish the bearing, not the bearing capacity, the whole capacity, the total capacity of this pile in terms of friction and bearing capacity. So this is the whole thing. So I will explain factor by factor what is every number in here. So, and we are going to consider, remember, the UK national annex reducing the capacity of the pile to cover our back. So the first number you have in here is basically the area of the shaft in the first layer. 0.3 is beta, and 38 is the average effective stress in the first layer. You can see here 38 kilonewton per square meter. The second term for the first part of the formula will be the area of the shaft in the second layer, 8S2, beta again, and in this case, we need to use the average effective stress in the middle of the second layer, 137. This factor 1.5 in here is a reduction of the capacity because this is a driven pile and we are reducing the shaft capacity because the friction. This other factor 1.4 in here is because we have to reduce the capacity because we are using an approximation, a model. So we always reducing 1.4, dividing by 1.4. In the second terms of the formula, or the last term of the formula, you have the area of the cross section of the pile because this is bearing capacity. This is NQ, the value we have as a data, and this is the effective stress, but at the base, because we are evaluating the bearing capacity at the base of the pile, so at the end of the pile. This factor 1.4 in here is again because we are using a model. And finally, this factor 1.7 is because we are evaluating in this term the capacity at the base of the pile. So we need to reduce with this factor 1.7 because this is a driven pile. If we have a bore pile, instead of having this 1.7 and 1.5, we're going to use in here, instead of 1.7, we're going to have a 2, and instead of 1.5, we're going to have 1.6. But in this case, we are using this number because this is a driven pile. We know that. So once you have calculated the capacity of the pile, you see in here split it in the capacity because the friction and capacity because the bearing capacity. You have a number in here in kilonewton. So 1,345 kilonewtons. So you can compare now the capacity with the design load you have, and in this case, it's a good condition.